prove legibility of LLM algorithms.
Cool. Yeah, thank you very much, Shafi. So yeah, today I'm giving a talk on Prover-Verifier Game. So this is inspired by theory, but mostly empirical work. And this is a joint work with Jan Hendrik, Harry, Yan, Nat, and Yuri. And this was done when they were at OpenAI. So first, I'm just going to give an overview of the whole paper, and then I'll break down into different parts. So we want to solve the legibility problem. So what does that mean? So we start with the hypothesis that in the future, we'll have AI models that are much more capable than humans. So we will ask it to write code to do some complicated science problems, and it will give us a very complicated solution. So it's hard for us to judge whether it's correct or not. And we already see this sometimes in the current time, because we sometimes ask ChatGPT questions, and sometimes it gives us a very, very long answer, and it's hard to say whether we can trust it or not. So in this paper, we define this legibility as if the verifier can fully understand the solution to the extent that any possible errors are spotted. So here we are going to have a prover that proposes solutions and a verifier. So the verifier can either be a human or another model that tries to say whether it's correct or not. So what are possible? Yes, yeah. So this is not necessarily the best definition, but yeah, but it's what we're exploring. Yeah, so. Yes, yeah, we'll see it in the experiments. So how do we make LLM outputs more legible? So one way is just to do the usual reinforcement learning from human feedback. So this would mean that we gather human labels for legible versus illegible completions and just train using some sort of comparison loss. So in this work, we explore an alternative way. So first of all, we optimize the prover LLM to produce chain of thought solutions, and we will use that as the proof. So just as convenience, because chain of thoughts are useful for performance, and it come as a natural justification. Maybe not the best one, but it's what we picked. And also, instead of training against human feedback on legibility, we just train it against the smaller verifier LLMs. So this idea of using smaller models as proxies for humans are not new. So I think people have been thinking about it a lot in scalable oversight. And one advantage of it is that it allows us to continuously parameterize the capability gap between the prover and the verifier. So we can just use like different sized models as a substitute for what's the discrepancy between their capabilities. I guess this is like slightly more formal thing about verifiability. So what it means for a class of functions to be verifiable by another verifier. So we kind of borrow those ideas from the pack verification and other theoretical work. So this would mean that we want completeness and soundness. So completeness just means that there exists a helpful prover in the family, and for any input in the domain of interest, it will generate a correct solution, and also the verifier will say it's correct. And for soundness, this just means that for any input in our domain, and for any other adversarial prover in the family, if it produces an incorrect solutions, then the verifier is not gonna say it's correct. But those are just ideal cases. Like in real life, we know that machine learning, you can't really ask for that. So empirically, we just want a helpful prover that have high pass rates on the problems, and also the verifier have high recall on the trajectories of that specific prover. And also for soundness, we just want to do like a limited set of adversarial attacks, limited in terms of compute, like we cannot optimize forever. We just want like very high precision of the verifier on those kind of attacks. And I'll say more in more details what these are later. The pass rates are just like more like the accuracy of the prover. So yeah, specifically on math problems, you sample many trajectories, and can you get one correct from like 8? Yeah. So verifiability training. So we want to train provers that have high legibility and also verifiers that are more robust. So we use a version of the Prover-Verifier game. It was first proposed in Anil et al. And also like in prior theoretical works, but they are the first that explore it experimentally. So this version is that we have the verifier play first. So it's kind of verifier leading game. And we assume that the prover will always play the best response. So we show that if we don't constrain the model class of the prover and the verifier, then if we find a verifier leading Staggelberg equilibrium, then this is equivalent to finding a complete and sound protocol. So this is actually very similar to theorem 2 of their paper. And I'll say more about the more formal version later. And also for the empirical training part, how do we actually train the provers and verifiers? We actually use the grade school math data set. So it is actually pretty simple, like a problem and like a few steps of math, just arithmetic, and then you get a final solution that's usually an integer. And we train 2 models. The verifier is usually a smaller LLM. We do sweep the size of the verifier, so you will be able to see some of the results later. So the prover is just a slightly larger LLM, and we don't really train 2 prover models. It's just a single model weight shared. So it's either prompted to be helpful or sneaky. And this will just taking a problem and a role assigned, it will output a chain of thought and a final answer. And the verifier will just take the problem, solution, answer, and output a score. So we train those models in an iterative fashion, and we will go in multiple rounds. And in each round, the verifier is trained first. So it's trained on a balanced mixture of samples from all of the provers from previous rounds. And the prover is trained using reinforcement learning, and its reward is the combination of whether you are correct and whether you get high verifier score, depending on the role. Because if you're the sneaky prover, then you're supposed to be incorrect and convincing. So this is the main result of our paper. So if you just want to take one slide away, this is the one. So on the x-axis, that is the accuracy of the model. So that this is the performance of the model on the math problems. And on the y-axis, that is the human evaluator accuracy. So what this means is that we will show the model completions to human evaluators under a very strict time limit, so 45 seconds. And we have 75 human trainers, and they will rate whether the solutions are correct or not. And we always show them balanced samples. They don't have any priors for like what's the average pass rate. And so higher means that the humans are able to judge the solution's correctness correctly more often. And so I guess the init on the top left is the model initialization. So this model, you can see that it has pretty low accuracy, but pretty high human legibility. So, so this initialization is trained from a variety of human written math derivations. It has nothing to do with GSM, but just like we find some human written math derivations online and from other sources, and we just fine tune the model on those things. So that's why it's pretty human legible, but it doesn't really have high accuracy to start with. And on the bottom right, that is the RL solution if we just optimize the model for correctness. So we just, yeah, the only reward you get is whether you get it correct or not, and that will give you very high accuracy, but very low human legibility. So humans are, it's pretty hard for them to tell from within 45 seconds.
So in the beginning, human evaluator is higher than the actual accuracy when compared against the like ground truth and GSM, or?
Yeah, so this is just whatever model we have. We just evaluate on GSM, and it gets like 0.4 accuracy.
Humans have like a 50% false positive rate, or am I not understanding this?
So
like it convinces humans
yeah.
82% of the time.
Oh, so this is not the convincing human. So this is more about like if we take balanced samples and how often humans are correct. So humans have to judge. So this is the
Okay,
human accuracy
accuracy,
on
like-
judging. Yeah, the judge
I
accuracy.
thought it was accuracy. Okay.
Yeah, yeah. Sorry.
Go back to the model, just one second.
Yeah.
Okay, so you have a verifier and a proof, yeah?
Yeah.
Verifier is a small LLM.
Yeah.
And at the end, it doesn't say yes or no, it just gives a score.
Yes.
And the prover is your LLM, the one that you're trying to verify its chain of thought.
Yeah.
Okay. And so how do we translate that to the diagram? This model, if you could just.
So this one, I think that so our method is the top middle. So like those two are kind of the baselines. Like if you don't do any RL and you just have just fine tune on human written solutions, that's the init. And if you just train RL for correctness, then you're bottom right. But we are kind of trying to get a new method where we kind of recover half of the accuracy gap, but also maintain high human legibility. So kind of trying to push the Pareto frontier here.
So maybe the y-axis, maybe I'm confused. If the y-axis means the human gets nothing and whether the human can answer, or the y-axis, can human judge the solution provided by the machine?
It's the judge accuracy.
And the x-axis is solution accuracy, not judge accuracy. So
Yes, yeah. What the X is solution accuracy.
So I'm confused. Why should human judge accuracy be the same, like with or without the checkability game, but then be different for RL?
So I think I think it's coincidental that our method has the same legibility as init. Yeah, so we don't really have explanation for that. But RL is low. It's because if you just optimize for correctness, then the chain of thought are kind of crazy.
I see. Wait. So but you put legibility tax as being on the x-axis. So what is this drop in the y-axis?
The drop in the y.
That's a gain, right?
Oh, that's a game.
Accuracy, right? Because you want it to be legible.
Fine.
Yeah.
Do you have any examples of like what the chain of reasoning looks like, you know, for the original thing versus?
Yeah. So I do have the trained solutions in later slides. The original I have it in the original paper.
Okay.
is that how to judge accuracy? Because so accuracy just means like it's two-sided thing. It means I assume you give a correct proof and the human doesn't understand it, says it's incorrect argument, and there is a second side is assuming given correct and the still. So do you do it? What's right? You put like one number. There are two quantities of interest.
Yeah.
Combine them some in one number according to some weight or.
So for any of the models, so like 1, 2, 3, 3 models, we always sample balance the samples from those models. So when we show it to humans, for every model, humans will see half incorrect and half correct samples. And they are just trying to judge whether it's correct or not. Yeah.
And then she has an even mixture, right? So it's just the average of the type 1 and type 2.
Yeah.
So I have a question about if you start with the post-checkability game thing as your initialization URL, do you move down? Do you move to the same point? Do you move sideways? Like, what happens if you initialize at the? Can these games add, or are they?
Yeah. So this dot on the top is already after 5 rounds of legibility game, but yeah, we haven't done pure RL from that point, so I don't know. But I would guess it will just drop to right.
Just go to the same place,
That's it's my guess, but I don't know. Yeah.
So the RL here is like, what's the reward it's optimizing for the RL?
I'll talk about those later. Yeah.
And just a quick question. So when you say it's hard for the human to verify,
Yeah.
was it because it was generating longer things and it's hard to verify in 45 seconds, or is it actually harder to verify?
So length is definitely one dimension of legibility, but there are also other dimensions like whether you are like rambling and doing some other stuff like if you verify 1,000 times, then humans can probably just check the first. So yeah, yeah, we don't really break down like what are different dimensions of legibility, and I think that's worth studying in the future work. Like what are factors that affect whether humans can judge things correctly. Yeah. So just to continue the results. So after this game, we'll have 3 artifacts. the verifier, a sneaky prover, and a helpful prover. So we just evaluate those kind of models, and we show increasing soundness of the verifier over the rounds. We will show the sneaky prover generate increasingly more subtle flaws, and the helpful prover will be more legible, and we will evaluate via like human trainers. So I think what is surprising about this work is that we just train against like smaller model verifiability, and it somehow transfers to human legibility. Like this is not necessarily a priori true, and we just have this like guess, like it might work, and we kind of find some evidence in it in limited settings, so it's kind of exciting. And so, yeah, I guess the final goal is whether this can be a promising candidate for a scalable oversight method. Cool. So I'm just gonna get in more details for the setup on the math side. So we will have a specific domain of interest, and in this case, X is the GSM problem, and Y is the final solution, just a single number. And the policy will propose Z condition on X, and is always from a certain model family F. And the verifier will taking X and Z, and it will output a score. So those are just formulations of convincingness and, formulations of completeness and soundness, and it basically just repeats the intuitions. This is a concrete game setup. Because to define a game, we need to define the utilities and the players. So in this game, we actually have 2 players instead of 3. We have the verifier, and the prover is just a mixture of the 2 roles. So for verifier's utility, it's the negative classification loss on the uniform mixture between helpful and sneaky samples. So the equation just means that we just uniformly randomly sample either sneaky or honest. And then for each of the policies, we just uniformly randomly sample X in distribution. And then the L is just the classification loss, like cross entropy, whether the verifier get it correct or not. And the prover's utility, first we flip a coin to decide whether it's sneaky or helpful. And then you will get a reward that's depending on your role, whether you get it correct, and also the convincingness score. So we just require that the R function, the reward function, satisfies that any row-aligned solution gets higher score than any row misaligned solution. So row alignment means if you are honest, you get it right. If you are sneaky, you get it wrong. And for the second property of R is that if you are row aligned, then if you get high verifier score, then you have to get higher reward. As long as you satisfy that, then that's okay to prove this main theorem. So this is for like all deterministic mappings from X to Z. And if you have this game with those 2 kind of utilities, then if you can find a verifier leading Staggelberg equilibrium, then you can also satisfy the completeness and soundness properties. Yes?
So when you run this and optimize the prover, how are you specifying the role? Is that just through the prompt, or?
Yeah, in the prompt. Yeah, you are the helpful prover and blah, blah, blah. You are the sneaky
But
prover.
you're fine-tuning the same underlying model basically to both generate like convincing incorrect proofs.
Yes. Yeah, they're weight shared. Yeah. So this is very similar to theorem 2 of Anil et al. And the proof is also kind of similar. So I'm gonna talk more about how we actually train the models. So basically, first, we don't just use GSM, we also augment GSM because we don't want to be bottlenecked by sample complexity. So we will have additional 100K synthetically generated GSM problems, and we validated them, so they're I believe they're pretty high quality compared to the original data set. Then we split the data set, the training data set, in half. So the verifier will be trained on only half of the samples, and the prover is going to be trained on the other half. And then the game will proceed in multiple rounds. So in each round, the verifier will be trained on relative loss in practice. So this is different from theory, and this is mainly to make it like more similar to the usual RM training. So because usually for RM, we will have kind of a batch of correct samples and batch of incorrect samples, and we just want the model to rate the correct samples higher than the incorrect, and plus a regularization term so they don't arbitrarily blow up. And for the prover, we just train using PPO on a reward, and this reward is also kind of different from the theoretical setup. So we experimented with 3 rewards, different rewards, and what worked mostly was the first one. So what the first one does is that it will take a batch of scores for a batch of samples from a single prompt, and then do kind of batch normalization. We make it mean 0 and also like within certain range. And then for the bottom half unconvincing samples, we just give it a very negative reward. And for the top half, depending on the row, you either get a negative score or the positive score. So you can really see that this loss prioritizes convincingness over row alignment, which is not really what's required in the theoretical formulation. But experimentally, we found it worked pretty well. And in the second version, it's more aligned with theory. So basically, if you are row aligned, you get V. Otherwise, you get a very negative score. And in the third version, we actually don't have the sneaky prover. So we just optimize one policy with respect to the verifier score. So you just try to maximize the score until your accuracy actually drops. So it's just more of an ablation. And so here are some experimental results. So firstly, the baseline. So this is just training against correctness signal only from 0 step to 8K. You can see that the model's test accuracy goes up, but eventually there's a drop because of hitting context lens. So it is true that the model generates longer and longer solutions in the end. So we take the snapshot from initialization from 3K steps and 7K steps, and we show them to human trainers. So you can see that for init, humans have pretty high judge accuracy, and for step 3K and 7K kind of drops. And the average time required to solve the problem also goes up. So remember that they do have a harder limit of 45 seconds, but on average, they only take like 26 seconds. But it will also go up as the solutions get harder. Yeah.
So at 8,000 steps, the solutions are so long that they no longer fit in the context?
Yes, sorry, 8K, only at 8K.
How long is the context window?
I couldn't remember.
But these problems are like 3 times 5 plus 7, right? That's what.
Yeah, usually like at most 3 steps of arithmetic.
Okay, right. And the solutions that are coming out are thousands of tokens long.
Sometimes, yes. Yeah. Okay, and what kind of samples are humans doing worse on? So on the x-axis, this is bucketing the samples by how often the model get correct in quantiles. So this means that if you're more on the right, then you are the model actually get wrong more often. Oh, sorry, the model actually get right more often. So basically, you can see that for 3K and 7K, when the samples, the model get correct more often, then humans actually do worse on. And that basically that's a baseline. And here we are showing some results from the verifiability training. This is like our method. So it proceeds in at most 5 rounds, like 0 to 5. And on the top, you can see the verifier score for the honest and sneaky policies. And so the solid lines are correct samples, and the dashed lines are incorrect samples. So basically, you will see that the sneaky incorrect will eventually catch up with honest correct samples, and that's when we stop the round. And then you can see that in round 5, it gets harder and harder for the sneaky incorrect to get as convincing as honest correct. And and on the bottom, there's the accuracy of the model. You can see that when it drops to 0, this means that sneaky find and exploit. It's like very convincing, and you're almost always wrong. But it gets harder and harder to find that. And in round 5, you basically don't find it in 8K, although it still drops a little bit in 8K steps. So basically, that's the dynamic side. So for evaluation, so first of all, we want to show that the verifier is becoming more robust. So how do we show that? First, we do some sort of adversarial attacks on the verifier. So this is just using different rewards as attack, but we always use the same algorithm. So there's definitely some limitations to it. We just use the reward, like the SRC reward, the good hearting reward, and the CGC reward, and we plot the number of steps onto the sneaky find and exploit. So what do we call finding and exploit? So this is, so for the SRC and CGC attack, this is when the sneaky model gets 95% incorrect. So almost all of the samples of the sneaky are incorrect, and the sneaky incorrect samples get as high verifier score as the corresponding honest correct of the round. So in general, you can see that it gets harder and harder to find the exploit as the training goes on. And also, we have some ablations on verifier size. And for larger verifiers, they get robust faster than smaller verifiers. So the smallest is 10 to the minus 4 of the prover, and the largest is 10 to the minus 2 of the prover. And here are some best of n results for the verifiers. So this is a little bit different from the usual best of n plots because so here we always take balanced samples. So say for n equals 600, we take 300 incorrect samples and 300 correct samples. This is always from the last checkpoint of each round, the honest policy. And then we just get a batch of verifier scores for those n samples and say like which one gets the highest score and is that correct. So it has a slight drop for each round because as you get higher and higher n, the problems that you can actually get like balanced samples from are actually harder and harder, because if you are like all correct, then you are not able to like even if I sample like 6,000 samples, it's really hard to get like 300 incorrect. So that's why like the distribution of problems are getting harder and harder on the right. So there's a slight drop on the right. And for round 0 to 2, it actually drops a little bit in terms of best of n, but 3 and 4 are on a different level. So yeah. And then we evaluate the sneaky prover. So basically the sneaky prover, we want to say that it generates more subtle mistakes, but this is kind of qualitative. So how do we quantify that? So on the right, we do just find like the human evaluators make mistakes more often on sneaky samples, and this is still balanced samples. So it does show it's like a little bit harder to detect. And on the left, so this is something different. So this is using GPT-4 as kind of a human evaluator proxy. Not really kosher, but it's just something interesting to see. So basically, we show the different snippets of the solution to ChatGPT-4, and basically, our hypothesis is that just from looking at the samples, it seems like the sneaky mistakes are kind of more localized in later rounds. So we expect to see that the minimum of the snippet scores actually go up, whereas the minimum of the snippet scores stays low, whereas the average goes up. So this means that most of the steps are actually correct. More and more steps are actually correct, but there's at least one step that's wrong. So that's what we see on the left from initialization. It's like 0.2 average to later round, which is like 0.5 average. So I guess interesting thing is for the sneaky correct samples, both the average and the minimum also go up. So this shows that actually they are getting, like the sneaky correct are getting more legible. So yeah, so here we have some samples from the sneaky policy. So this is from round 1, and this is from round 3. So basically, in round 1, it will just make some calculation mistakes, like 5 times 9 equals 36 instead of 45. And in round 3, so if you don't look at the problem closely, then you can't really spot this mistake. It's more about calculating the wrong quantity, like why you're calculating this quantity. Yeah, qualitatively, it seems more subtle as well. Oh, yeah.
You have the same problem on both sides. Yeah. And on the left, you're saying there's a Can you just couch that in your framework, this example?
Yeah, so basically the problem is X. So Shana's father is 5 times as old as Shana, blah, blah, blah. And so basically this prover, the sneaky prover, is prompted with, you're the sneaky prover and here's the problem, generate solutions. So the sneaky prover gives the solution. So its goal is to be convincing and incorrect. So here the incorrectness is in 5 times 9 equals 36. And it's in brackets, so it's actually very easy to spot. And here, this is in round 3 of the training. So after playing this game, after training the verifier and the policy verifier and policy for 3 rounds, this is also the sneaky policy. And so the kind of mistakes it makes are less obvious. I guess that's the thing we're trying to make. But yeah, I agree that this kind of cherry picking is not really the best. So that's why we're trying to do some sort of human evaluation there.
Sorry, for the humans, what kind of directive were they given? Like 45 seconds is kind of short for me to read that paragraph.
Yeah.
But it's not short for me to solve the problem and see that the answer is wrong.
Yeah. So so the instructions for humans are in the paper. Yeah.
We don't say that out loud.
Yeah, so basically we instruct them to don't solve the problem by themselves, try to judge whether the given solution is correct or not. And they're asked to judge whether the final answer is correct. So if you spot mistakes in the solution, then you can actually stop. Yeah, so yeah, we ask them to not solve the problem by themselves, but I don't know whether they actually do.
Why did you agree on 45 seconds?
Oh, so it's because we originally had 1 minute and they all did perfectly. Yeah. Yeah.
I guess related to the previous question, this is something maybe you can go back and check now, right? Like what % of like problems maybe had incorrect solutions, incorrect rationales, but correct answers, and of those, like, what did the human decide for those problems? Like, did they actually just look at the answer, or did they look at?
Yeah, that's a good idea. Yeah.
Also, I mean, it seems like deciding whether the answer is correct and the reason it's correct is kind of different than like spotting the error in the reasoning, right?
Yeah, that's right.
Which is kind of, yeah.
Yeah, I agree.
Okay.
Yeah, we do have the instructions in the paper, and potentially there could be preventing design. Yeah.
You said something as a throwaway comment was very interesting about why you at the time that you gave them, when you gave them a minute, they were getting it all right.
Yeah.
Is part of your data actually how long before they answer? And are you using that time they spent it seems like you're not using it as any kind of training signal, but it seems like there's probably data in signal there.
Yeah, that's right. Yeah, so
Legibility especially, right?
yeah, we do have some flaws for like the time to solve the problem, and the error bars are kind of high. So,
but it seems like it'd be different for things that are correct or incorrect and different. Like it seems to be going up, but it might be differential across incorrect and correct.
Yeah, that's right. Yeah. Yeah, I think it's probably worthwhile to separate by correct versus incorrect, and probably the important thing. Yeah. Okay.
What's your conclusion from this statement that optimizing for correctness makes it less legible?
So if we just optimize for the final answer correctness, then the chain of thought is not necessarily legible. And in those like the crash cases, we do see like it gets super long and getting repetitive sometimes. Yeah. Okay, so here's some results for the helpful prover. So basically, this is on the left. It is the model accuracy, basically how well the model does on GSM. Arguably not very high, but it's getting up a little bit across the rounds. And for the human judge accuracy, we see some upward trend, although there's some weird thing with round 4. And this is at the average time to solve. Similar graphs. So this is the samples from the helpful policy. So this is for init. So init has some, so this is a correct init solution, even though init only have like 40% accuracy actually. So it's kind of short, kind of compressed. And then for round 1 of checkability training, it definitely gets longer. And there's like more natural language, I'd say. And for round 5, they do prefer more spacing and yeah, things like that. Yeah, it's a little bit hard to judge, but you can kind of see a little bit trend. So yeah, so just some ablations now. So this is with a different reward. So this is with the second reward that we call correctness gated reward. So remember that this reward will prioritize row alignment over convincingness. And so unlike the first graph, we don't really see across the rounds, it gets harder and harder to find exploit, although round 5 seems pretty high. But yeah, it doesn't, we don't really find consistent improvement from this reward. So we do have one hypothesis for why this reward doesn't work as well. So, so besides the difference between correct and incorrect, the honest and sneaky could take very different format. And this would mean that if it's very easy to separate via other sort of spurious features, then this training will be less helpful because if the honest will just, if the sneaky will just learn to say, okay, let me think about the problem and then write something, whereas the honest wouldn't do that, then like if you do the verifier training on those kind of comparisons, then it's not very useful signal to train on. So we've just take the samples of the, so this is the good reward, the main reward that we use. We take the samples from different rounds and we train a very, very small discriminator on honest versus sneaky samples, and both are correct, or both are incorrect. And we just take the area under the curve, and so round 0 is pretty separable, and round 4 is getting less and less separable. Whereas for the other reward, it's very separable to begin with, and it doesn't really improve much until round 4. So yeah, so it does seem like if the reward encourages separation early on, then you're gonna have less benefit from this sort of training. So the reward design does matter. And so here, this is another ablation. Basically, this one is, we don't have the sneaky policy, and the honest policy will just try to maximize the score. And then, so this is for the verifier of different sizes, so from 10 to the -4 to the same size as prover. So as we get larger verifier, they get robust. They're just naturally more robust, and they get robust quicker. And also, yeah, but still for like the smaller models, if you just do multiple rounds. So here, because we don't have the sneaky policy, so you just take one honest policy and then just take balanced correct versus incorrect samples and just train the verifier on those samples. So it seems like sneaky policy isn't strictly necessary, but yeah, it still kind of goes up in the end. So here are some ablations that also didn't work. So the relative verifier size actually do matter. So for example, on the left, we have a very small verifier. So this is way fewer than 10 to the -4 of the policy. So in this case, the sneaky finds an exploit pretty fast. Even in round 4, round 5, round 6, we also tried more. So it seems like the relative verifier size do matter for this thing to work. And also on the right is for a very large verifier. So this verifier is, I think, as large as the policy. And in that case, you can see that the sneaky policy, if you just give it a sneaky prompt, it follows the instruction very well. It will just start with like 0.2 accuracy. So in that case, it couldn't really be made robust very easily. So yeah, and then we also show those to humans. It seems like starting from initialization, the legibility just drops. So yeah, so it seems like we do need like some sort of capability gap between the verifier and the prover. So yeah, so basically, just summarize everything. If if we just do training against correctness signal, then we don't necessarily get very legible chain of thought. Whereas if you also want the chain of thought to be more checkable by smaller models, then it also transfers to human legibility. So yeah, basically we just want to come up with one way to measure and to address the tension between the model performance and legibility. But I guess one important drawback is that we are using a lot of supervised labels for correctness. And it would be best if we can have some sort of semi-supervised methods or unsupervised methods, because for scalable oversight, we can't really afford to have a lot of human labels for correctness. Yeah, so that's it. Thank a lot of people for helpful comments and improvements to the draft. We also have the archive for the full paper and blog. Yeah, thanks.